and my specialization was propulsion. Right. So this the class notes, anything can be found either in the references are taken from Modern Compressible Flow by J.D. Anderson as well as NPTEL. So the prerequisites are just the normal shock problems and a few the basic thermodynamic principles, right? So as we all know that if I have a stationary shock and if there is a velocity u1 uh, across the normal shock, my pressure, my temperature, and my density increases. That is, it increases the flow, pressure, temperature, and density. So this is the funda for the stationary shock wave. And then for moving shock wave, in this in the both problems, I'm dealing with the lab reference frame, right? So I am observing it from somewhere here, and I'm seeing that here the shock is stationary, and here my shock is moving, and it is moving with the velocity w into a stagnant gas which is ahead. So if I am taking a small CV, so in this part, the air in this region is stagnant, whereas here, due to the moment of the shock, there will be some velocity induced behind the shock, which I am telling it as UP, and it is called generally as piston velocity. Right. So there are many applications. There are many physical applications of moving shocks, or so you can see the applications. The physical applications are there in our hypersonic wind tunnels, which use the shock tube concept, which use a shock tube concept for testing the re-entry vehicles or any hypersonic applications where my mark is more than 5, right? So for these applications, my subsonic and supersonic wind tunnels don't suffice, and shock tube tunnels are mostly used. Shock tube or shock tunnels are mostly used. So there, the time of operation is in the order of milliseconds, but still uh, using high frame rate cameras and using shadowgraphy methods, they find the properties or the pressure temperature values of the testing vehicle. And also it is used in our pencil industries to dry the woods. So these woods typically take days to get dried. So using these shock, moving shock problems, you can do it in a matter of minutes to hours, right? And you can also use. There are medical applications of this moving shocks also, mostly in visualizing or seeing whether there are presence of kidney stones are there or not, right? So, so mostly we are interested in the shock tube or the shock tunnel problem. So shock tube tunnel, so it's basically a constant diameter tube almost, and it is divided by a diaphragm. So this is my diaphragm. So this diaphragm can be anything. Sometimes they use thin sheets of metal in which some engraving is there. So there will be some engraving, so that when I pressurize my driver section. So this driver section will be of very high pressure, of orders of 50s to hundreds of bars. So to at a certain pressure, this diaphragm will burst, and it will lead to a since from my high pressure to low pressure, there is a normal shock which starts moving, and towards my right there will be a normal shock, and towards my left there will be a series of expansion waves that will be propagating, right? And a small line which is at the starting, which is here, will be moving with an induced velocity up, which is induced by the normal shock, right? So here, if you see, my pressure distance curve will be something like this. It's just a step function, and once it bursts, there will be a decrease in pressure, and then due to the since it's the initial pressure is P1, uh, the pressure ahead of the behind the shock will be higher. So just at this location, my pressure will drop, and in the expansion region, it will increase to P4. So this is a typical pressure distance curve of a shock tube, and so if so, generally, this is my shock tube, and it is moving into this region, right? So, and here it is stationary, and a UP is induced, right? When I am looking it from this perspective, from the laboratory frame of reference. But if I transform this to an inertial frame of reference, that is, if I'm standing on the wave, so if I'm standing on the shock and I'm witnessing these values, then I'll see that the fluid is ahead of the shock in the region 1 is moving towards me with a velocity W, and it is and the induced velocity will have a value equals to W minus UP. Right? So this is my funda. So this is my inertial reference. So any moving shock problem, first we'll transform it to an inertial problem in which I'm standing on the shock and I'm seeing that the velocity is coming towards me from region 1, and in region 2 it is the relative velocity W minus UP. So this part is clear, right? This relative velocity part. So it's just like the CFD problems that we take, right? If there is an airplane which is moving with a velocity v, so this we transform it as the same aircraft which is stationary, and my fluid is coming at me with a velocity v, right? So the same funda is here. So we'll derive some relations for the moving shock problem. And okay, so for my stationary shock, for my stationary shock, my continuity was rho1 u1 is equals to rho2 u2, right? And so for a stationary shock, matlab, this I am talking about. So here my density is 1 p1 t2 rho2, right? So and my momentum will be p1 plus rho1 u1 square is equals to p2 plus rho2 u2 square. And similarly, my energy will be h1 plus u1 square by 2 is equals to h2 plus u2 square by 2. So if I'm for a moving shock, for a moving shock, if it is moving with the velocity w, if the shock is moving with the velocity w, and the induced velocity is up in the laboratory frame, and so I convert this into a inertial frame, right? So I'll see that, yeah. So this, when I convert this into inertial frame, then it becomes again a stationary shock problem, right? So with respect to the inertial frame, my shock is like stationary, and from the region one, my velocity is w, and in my region two, my velocity is w minus up. So instead of u1, I'll plug in w minus up, and sorry, instead of u1, I'll be placing w, and instead of u2, I'll be putting w minus up. And the same set of equations, and if I write the same set of equations, they become rho 1 w is equals to rho 2 into w minus up, and p1 plus rho 1 w1 w square is equals to p2 plus rho 2 into w minus up whole square, and h1 plus w square by 2 is equals to h2 plus w minus up whole square by 2. So let's say this is 1, this is 2, this is 3. These equations are 4, 5, 6, right? So I hope this is clear till this point. And if I'm taking from my continuity equation, I can write my w minus up as w into rho 1 by rho 2, right? So from these equations, I'll be just substituting this 7 in 5 and 7 in 6, and writing this 4 as in terms of w. So I'll be doing that, and I'll be arriving at our usual Hyogonite equation, and we'll see how different it is from the stationary normal shock problem, right? So plugging this 7 into this 7 into my 5, so putting my 7 in equation 5 in the momentum equation, I will get p1 plus 1 w square is equals to p1 p2 plus rho 2 into w rho 2 by rho 1 whole square, right? So if I rearrange and put it in terms of w, so my w square will be nothing but p2 minus p1 by rho 2 minus rho 1 into rho 2 by rho 1. So this I'll put it as 8. And from the same continuity equation, I can write w is nothing but rho w minus up into rho 2 by rho 1, right? So I'm writing w as rho 2 by rho 1 into w. So from continuity, I'll write w is rho 2 by rho 1 into w minus up. So now again I'll plug this in. I'll substitute this equation in phi. That is nothing but my momentum equation, right? So again, my equation will be the form. So w minus up whole square into rho 2 by rho 1 whole square is equals to p2 minus p1 by rho 2 minus rho 1. sorry, putting this equation in equation 8. Sorry. So putting this in equation 8, I'll be getting, instead of W, I'll be putting rho 2 by rho 1 by W minus P whole square. And the on the RHS, the equation remains same. This will lead, so my W minus UP whole square will give me a RHS value, which is solely a function of density and pressure. This I put it as 9. So, so I have my W minus P and have my W square. So both velocity and my relative velocity in the both upstream and downstream of the shock, I have it in terms of P2 and pressure and density, right? So if I plug this both in my Hugonoid equation, I'll be eliminating the W minus UP and W terms, right? So my E1 plus P1 by rho 1 plus half W square, right? So W square, I will write it as P2 minus P1 by rho 2 minus rho 1 into rho 2 by rho 1. And E2 plus, so these are my enthalpies, right? E1 and E2 are my enthalpies. P2 by rho 2 plus half into P2 minus P1 by rho 2 minus rho 1 into rho 1 by rho 2. Right. So if I simplify this, I'll get my change in enthalpies.
Yeah. Yes, Dheeraj, you can, since it's a crash course demo, so we can write quickly final derivation also. Because during
Okay, sir.
classes, we will not derive because it will be a short-term course. Okay.
Correct, sir. Oh,
Yes.
okay. So, so this is the usual Hugonoid equation. So this is our Hugonoid equation, and this is, if the observation that can be made is that it is same as that we derived for stationary shock problem, right? So for a moving shock or a stationary shock, my Hugonoid equation remains same. So anyways, if I have to again get those ratios, right? We find P2 by P1, T2 by T1, rho 2 by rho 1. So these equations, to find these equations, the three equations have to be solved numerically. So these have to be solved numerically. But if we assume that it is a calorically perfect gas, then I can substitute in E, I can substitute CV into T. So this will come as a function of CV into T2 minus T1. And this will be as it is. And using the ideal gas law, that is P is equals to rho RT, I can get everything in terms of temperature. And I finally get that my temperature ratio will be P2 by P1 into gamma plus 1 by gamma minus 1 plus P2 by P1 by 1 plus gamma plus 1 by gamma minus 1 into P2 by P1. Right. And similarly, I get my rho 2 by rho 1 as 1 plus gamma minus 1 by gamma plus 1 by gamma minus 1 by gamma plus 1 plus P2 by P1. So these equations, so it's not necessary that you remember these equations. But if at all it is required, any problem, any moving shock problem can be converted into a stationary shock problem and can be seen as the normal shock problem that we generally see. So the same normal shock tables can be used. So, but by chance, if in exam they have to, if they ask you to find these equations or the values, then probably and hopefully they'll give these equations, right? So one important observation that can be made is that in seeing these two equations for a stationary problem, my T2 by T1, P2 by P1, rho 2 by rho 1 were a function of one gamma and my M1 only. That is my upstream Mach number, right? But here, for a moving shock, these values are a function of gamma and my pressure ratio. So what is my pressure ratio? So this is my pressure ratio, P4 by P1 or anything, P2 by P1, right? So this pressure ratio dictates that how strong my shock is and what are my downstream or the upstream temperatures, right? So that is one important observation that we can make. So if we come to the limiting value of UP, so if my shock that is traveling with the velocity W and it is inducing the shock UP, can anyone tell me that UP can be supersonic? Can it be supersonic at any point of time? Can UP be supersonic? Can it have supersonic velocities? So for that, we'll have to use the limits of. So if what happens if my P2 by P1 reaches infinity? At this point, can UP be supersonic? So to see that, to see that, my UP can be defined as so my UP. So from the same continuity equations and all, and from the momentum equations, I can derive my UP, which is nothing but A1 by gamma into P2 by P1 minus 1 into this term, right? So this is also a function of gamma, P2 by P1, and A1. So A1 is the speed of sound in this region, in the region that in which in the direction in which the normal shock is propagating. So, so let the Mach number of the induced motion be MP, that is nothing but UP by A2. So if since it is in region 2, my Mach number of the propagating gas will be UP by A2. So my A2 is nothing but root over gamma R T2. So substituting that, so I can write my UP by A2, which is nothing but my Mach number, as UP by A1 into A1 by A2, because A1 and A1 will get cancelled. So UP by A1 and A1 by A2 is nothing but, so since my A is root over gamma RT, my A1 by A2 remains T1 by T2, right? So here my UP by A2 again is equals to, I'll substitute the formula of UP by A1, which we have seen here, into this equation, and the T1 by T2 or T2 by T1 that we have seen in the previous slide in this equation, and I get my Mach number. And if I put my P2 by P1 as infinity, that is, if I divide and do some operations among these values, then I will see that my UP by A2 turns out to be 2 by gamma into gamma minus 1. So for this, for a gamma is equals to 1.4 that we generally take my this value MP, that is UP by A2, reaches a value of 1.89. So yes, it can go supersonic for certain certain pressure ratios. Correct. So if I place a body inside the shock tunnel, and if a shock is moving towards it with a velocity W, it will hit and it will pass through it, and again it will see a strong gust of wind of a value UP again flowing at towards it, right? So this is one important. So the crucial observation that can be made is that in a stationary shock problem, M1 was the government parameter, whereas in the moving shock problem, the P2 my P1 dictates my the temperature ratios, the pressure ratios, and whatever flow parameters are there, right? So and also for a stagnation or a total enthalpy is constant for a stationary shock problem. That is when we put a stationary shock problem and from 1 to 2. So here my H naught 1 will be equals to H naught 2, as we have seen in the normal shock relations, right? But in my in my moving shock, my region 1 is stagnant, right? So my H naught 1 is nothing but H1. And H2, because of these induced velocities and high pressures, the temperatures will also be high. My H is nothing but Cp into T, right? H is equals to Cp into T. So here, obviously, my T2 will be greater than T1, right? So my H2 is greater than H1 for sure. And if I'm writing my total quantities, that is H2 plus UP square by 2 is equals to H1 plus, since this air is stagnant, my velocity in this part of the region will be 0, right? So my H naught 2 will be greater than H naught 2 bar, right? So this is one important observation. And we'll see some problems related to this moving shock problem. So this is a previous year question. So and this was a nice question, and many people had some ambiguity solving this question. So that's why I taken up this question. So they are saying a shock moving into a stationary gas can be transformed to a stationary shock by a change in reference frame, as we have seen before also. So which of the following is or are true relating the flow parameters in the two reference frames? So uh, if this they are saying this shock is moving with a velocity vs and it is transformed to a stationary shock, so this is a stationary shock, and so for this my vs the air will be flowing towards it, right? So here this part of the region is stagnant, right? So okay, so let's say this is case 1 and this is case 2, right? For case 1, my p naught 1 will be equals to p1, right? Since my velocity is 0, the air is stagnant, right? And in my case 2, and also my temperature will be T1. So my total properties and my static properties will be same because the air is stagnant, right? So And in my case 2, I can write my T01 is equals to T1 dash plus Vs square by 2Cp. And my P01 dash as P1 dash plus Vs square by 2Cp. So here, my fluid is the same, right? So this fluid and this fluid is the same. So my pressure, my temperature, my densities will be same, right? So here my T1 dash is nothing but my T1 here, and P1 dash is nothing but my T1 here. Only there will be a change in the total properties, because here my air is stagnant and here my air is not stagnant, right? So static properties will remain same. So here they have given that T1 is greater than T1 dash is greater than T1 and T1 dash is so. These both options we can rule out. So we are left with only these two options. So let's see further. So they are here comparing the T2 dash, that is the temperature after the shock of case 2, with that of temperature before the shock of case. So if you are considering T2 and T1, so let's see for case 2. So for case 2, again for across normal shock, my P2 dash will be greater than P1 dash. My T2 dash will be greater than T1 dash. My rho 2 dash will be greater than rho 1 dash. Correct. So my T01 dash, which we have seen that it is T1 plus T1 dash plus Vs square by 2Cp. So this is nothing but T1, right? So T1 plus Vs square by 2Cp. So of course, my T01 dash will always be greater than T1, because Vs is not zero. Since Vs is not zero, or it cannot be negative, and this whole quantity cannot be negative, right? So my T01 dash is always greater than T1. So, and my T1 is nothing but my T1 dash, right? Okay, so here, uh,
Anyone
sorry,
have
did
any doubt, guys?
anyone has any doubt?
Joy, Saran, Vamsi, Akash. Are you guys understanding? Mahi, Ayush. So there is keep asking questions and asking for response also. So that's where
Right.
it will become more interactive. Vamsi, any doubt? Saran, Akash, Johit. Since we keep at
Uh,
IGC classes interactive, so I always prefer and ask IGC team to interact as much as possible from our side, and then they
yes.
can also ask more doubts during
Also, if
classes. It's
correct. So if it's not by audio, you can just type your queries in the chat box also. So that way the class can be made more interactive.
used.
So have you guys
Use
solved this question before? Yeah, or did anyone come across this problem before?
Let me ask one more question. How many of you have already read Gas Dynamics? Akash, Johit, Sharan, Vamsi. How many of you have read Gas Dynamics? Mahai, Ayush, and those who are watching this session on YT can also tell. Quickly, guys, please respond.
Please type in the chat box.
First time. Okay, Ayush. So there are multiple things which we cover before moving to gas dynamics, specifically moving shock wave topics. Before that, thermo basics and then GD basics are done. Okay, especially conservation equations and all. Uh, then we come to this. Okay, so, are you understanding, Ayush, what we are discussing? But before that, you should know normal shock wave equations for governing equations for SAM. Then only you can relate this topic with, you know,
Correct. So these equations must be known. Once we know these equations, then it will become easy for you.
yeah. And these equations comes from basic fluid and aerodynamics. So before gas dynamics or before aerodynamics, we always cover these equations well. Yeah. Fine. I think they need to brush all these basics, Dheeraj. No problem. Let's move to that problem.
Correct, sir. So so here they are comparing T2 dash and T naught dash, right? So here my T2 dash in if I say see in case 2, my T2 dash will always be greater than T1 dash because if you see normal shock or the stationary shock problems across when I move upstream of the flow, that is across the shock, my pressure, temperature, density increases, right? So my static quantities always increase. So my T2 dash will always be greater than T1 dash. And here we have seen that my T1 dash is nothing but T1. So it will be greater than T1. And since in this part of my flow my air is stagnant, this is my T1 is nothing but my T naught 1, right? So T2 dash will be greater than T naught 1 and not less than T naught. So this also cannot be my option. So once you guys are familiar with all these topics, then you can also see that P2 is greater than P naught 1 and T naught 1 dash. So these are easy to get once you correlate all these terms, right? So we'll see one more problem in this. This must be the easy problem. So So they are saying a strong normal shock with a pressure ratio of 29 across it is traveling into the stationary air at T is equals to 280 Kelvin in a straight duct. The magnitude of the velocity of the air induced behind the shock. So you basically have to find UP. And you need not remember the huge formula of UT that we have derived. You can use your continuity and momentum equations to find not even the momentum. Continuity is enough. So the problem is this. So there is some shock which is moving with a velocity Vs into stationary air. Let's say this region is 1 and this region is 2, and it is inducing a velocity UP. So this is the moving shock. And if I convert into a stationary shock problem, so I'll see that the air is coming at me at with a velocity Vs, and this will be the induced velocity will be Vs minus. So stationary. So any move because these moving shock problems we are seeing that they are giving more frequently, at least one right in the recent years. So that's why this topic has been picked for today's crash course. And this is also a recent problem. Came in gate 2020 or something. So if I convert into a stationary shock problem, then it becomes an easy problem, right? So if you see your gas tables, so if you see your gas tables and see that if you see your normal shock relations, you will be knowing what is for a particular Mach number, what will be my what will be my T2 by T1, my P2 by P1, and my rho 2 by rho 1. So these quantities can be directly taken from the gas tables, which is also allowed in the gate examination. So here they have given me that P2 by P1 is 29, and my rho 2 by rho 1 is we have to find. Right? So if I find for my they have given me pressure ratio. So from this, I get my Mach number to be. Can anyone tell me what is my Mach number? Take gamma is equals to 1.4 and P2 by P1 is given 29. Can anyone tell me what is my Mach number? So if you solve this equation, you will get your Mach number to be 5. And if I put in this 5 in this equation, my density will be also 5. Right. So my MS, that is my Mach number of the shock, will be nothing but my Vs by A1. Right. So this will be, so my A1 is nothing but root over gamma R T. So Vs is A1 is root over gamma R T1, which is nothing but my moving shock pi. So Vs is nothing but pi into root over 1.4 into 288, 287 into 280. So if I solve this, I'll get a Vs to be 1677 meter per second. And from continuity, from continuity, that is by rho 1 u1 is equals to root 2 u2. And I'm putting this in equation, this terminology. So I'll be getting W is equals to root 2 into Vs minus, sorry, this is Vs. So I know my Vs, I know my rho 2 by rho 1. I just have to find my UP. Can anyone tell me what is my UP? So you have everything. You have rho 2 by rho 1, you have Vs. So you just have to find UP.
You mean velocity?
So if you write the formula, it is Vs by 1 minus rho 1 by rho 2. Just by rearranging these terms, right? So this is my answer. So can you guys calculate and tell me quickly what is my UP? Okay. The value should come around 1341.6 meter per second. 1341.6 meter per second. So there is one more topic that I would like to discuss. So it's the continuation of the same topic. It is the continuation of same topic. So it's called. So once my shock, which is there, once it is traveling with a velocity, let's say W or Vs, and the induced is UP, right? And once it reaches this end, so in this end, my velocity cannot be UP at this boundary condition. So at this boundary, my velocity normal to the wall should always be zero. If you have seen the, or if you have taken the aerodynamics courses, then you can see that the normal component of velocity cannot be more than zero, or it has to be zero, right? So once my shock reaches, or it is about to reach here, my induced velocity will be UP, right? So, but I cannot, this ball cannot take UP. So what it does is that it sends a normal shock propagating back into the fluid, so that the velocity of that, the induced velocity of that shock cancels the UP and makes this wall boundary condition, that is my wall boundary condition, that is the velocity at that wall, to be zero. So if we see, if there is a shock that is traveling like this with a velocity W and induced velocity UP, after reaching this, it will hit this wall and it will reflect a wave in the opposite manner, in the opposite. So if I say this is 1, this is 2, so this will be 2, and this will be 5. So I'm just naming this 5 so that it will be clearer. So it will be, let's say, the velocity of this shock is WR, and of course there will be the existing induced velocity that was induced by the initial propagating normal shock, right? So here in this part, my U is 0, and also in this part, my U should be 0, right? So U5 will be 0. So this is how the nature will adjust itself, that my velocity remains 0 at the boundary of the shock tube, right? So again, if I convert this into a normal shock problem, so stationary normal shock problem, then if I put an observer here, so these are in reference frames, right? These velocities are with respect to someone who's standing, who's observing the whole thing, right? So if I say place the same observer on the shock, then he will see that this is my WR and this is my UP plus WR, because UP and W are moving in the same direction. Then for my observer, he will see higher velocity than the one that is observed by this guy, right? So similarly, if we apply the continuity equations, we should be able to solve these problems, right? So these will be my continuity equations. P5 plus rho phi into WR square and H2, that is my energy. This is my continuity. This is my momentum. And this is my energy equation. So this is the same thing that we have done, but the important concept is that there will be a reflected shock wave that will cancel out the induced velocity near the bound and make my U5 to be 0. Right. So we can stop, sir. I think I'm done with the concept, sir.
Yeah, we can mind.
So this is what
Yeah,
I wanted to
yeah,
share.
yeah, sure. So, any doubt, Vamsi, Saran,
Yes. Any doubts?
Rohit, Ayush, Mahi, Kanish? Anyone have any doubt? Yeah, so these are just glimpses of our classes. Uh, we start always classes from scratch, basics, and then further we move to all these core topics of aerospace engineering. Okay, guys. So when we start classes from November 5th, we will be starting with fluid basics, engineering mathematics, and then engineering mechanics comes solid mechanics, and then later once like fluid basics are done we will start aero and subsequently we'll start gas dynamics. Okay, so that will be subject sequence, and when once like we are done with this solid mechanics, then we'll be moving to thin wall structures and mechanical vibration, and after math we usually starts like flight mechanics and other part of jet propulsion. So November month mostly will be try to finish basically basic subjects, and December will be taken core subjects for this crash course, and January will be first week there will be classes, and then subsequently mock solutions classes will be there throughout January, and Feb hopefully second week of now I think third week of Feb we have exam. Yet final dates have not come. Yeah. So thank you, Dheeraj, for your
Right.
time. And can you move to last slides and then we'll wind up.
So this
So thank you, Dheeraj. Let's wind up this.
right.